Hi guys, as promised, in this video I'm gonna show you my own take at achieving a convincing grass wind animation. Before starting, I want to illustrate the rules I imposed to my approach, to have a direction on which I could base it, like a real work scenario. I wanted every part of the shader to be entirely procedural, so no backend data in vertex color, UVs or textures. Everything is obtained with pure math. For how much it was possible, I tried to replicate as realistically as possible the movement of a grass blade moved by the wind. So, I tried to keep the stylizations to a minimum. Because of those conditions, I also chose to just model the bare minimum required for the mesh to be animated, which is just a tessellated vertical rectangle. Moreover, given these constraints, I ended up creating a next-gen animation, which is a cool way of saying that I didn't care too much about performances this time. But it didn't came out too bad after all, consider that I'm running this scene on an old 980 Ti. So with that off the way, let's jump right into it. The very foundation of my shader is the way I bend the mesh. Once done that in a convincing way, it's just a matter of getting the oscillations right. So, how to procedurally bend the mesh in a way that feels realistic enough and, not less important, the calculations required are actually implementable? After testing out some stuff, and trust me, I did test out some stuff, the best way I was able to find is to imagine the grass blade as a vertical segment and remap it along a quarter of circumference. Even though I'm still convinced that parabolas or ellipses would have been better shapes visually, the circle has trigonometry on its side, which makes everything much more doable. Let's elaborate a bit more on this idea then. What does it mean to imagine the grass blade as a segment and then remap it on a quarter of circumference? Let's imagine this line as our grass blade. You can imagine the vertices that compose the mesh to be somewhere along this line. Now, imagine to have a quarter of circumference that is tangent to the base of this segment. I want these vertices to find their place on that, like the midpoint on the mid, the quarter point at a quarter, etc. And that will do for the arriving position. But what about during the in-between? How can we calculate the vertices position when the, let's call it, bend intensity is not a full power? In other words, what's the path those points have to follow to go from the segment to the circumference section? We could naively think about linearly interpolating the two positions, which would definitely do the job, but it wouldn't be accurate. See, if I draw straight lines from the start position to the end position, we can easily see that the length of the leaf wouldn't be preserved. Actually, you could clearly see it if I was precise enough with my draw, but trust me on that. It will become shorter while it travels, to bounce back at its correct length towards the end. We should rather look for some curves to use as path for these points. After many tests and tears, as I was showing earlier, I came up with a neat trick to solve the problem. If we make the circumference progressively bigger and bigger, and its section on which to remap the segment on smaller and smaller, it gradually approximates to a straight line, which would eventually become identical to our starting segment. And that's the theory, which looks like something that should work. But now the question is, how the hell do we implement such thing? Let's imagine that our grass leaf has a generic height that we'll call h. And it's located in the world at an origin O. We know that this segment must be remapped along a quarter of circumference, a section of circle that we'll call S. Since the segment has to cover the entire circle section and keep its length constant, it means that the two lines must have the same length, which means that h equals s. Another thing that we need to know is where this circumference is located in the world, where its center, C, lies on. For how we decided to position this circle earlier, we know that its y position is equal to the grass blade origin. And since we're talking about a circle, we can assume its x component will be origins x plus the radius r of the circumference. To know what the radius value is, we can do some simple math. We know that the perimeter of a circle is calculated by multiplying the radius by 2 pi, which means that if we know the perimeter and we want to calculate the radius, we have to divide the first by 2 pi. Now, since we know how long a quarter of that perimeter is, we can say that 4 times that divided by 2 pi equals r, which simplifies to r equals 2h over pi. Let's see if everything did so far actually works. This amazing website lets us to plot every function we want in a nice and interactive way. Let's bring all our formulas here and see what we get. Looks like it's working as it should. If you remember though, we said that the circle should get bigger and bigger and further to animate the grass blade properly, but now we just have a fixed value which stands for the completely bent state. This means we need to be able to shoot the center of the circumference from here to infinity at will, which means the value of the radius has to be free to move. Moreover, given this, it also means that the length of our segment h won't always be equal to a quarter of circumference, but to a section that gets smaller and smaller with the increasing of r. So, what we need now to understand, depending on the radius value, how long the quarter of circumference S is. We can do that by returning on the equation we used to calculate r in the first place and putting 4s instead of p, and simplifying. Okay, we remixed things a bit and we are almost ready to move to the next step. One thing that I want to fix first is the range of R. Having a parameter that goes from 0 to infinity makes playing with the graph quite uncomfortable, and will make uncomfortable tuning the shader in Unreal afterwards too. Wouldn't it be much better if we had a bending parameter called B that ranges from 0 to 1 and linearly controls the animation? To do that, we have to change our mind again, sorry about that, and express once again the radius as a function of h, and add the parameter b to it. Dividing for a number between 0 and 1, such as b, makes the result bigger and shoot to infinity the closer the parameter gets to 0. Moreover, by rewriting once again the value of s as a function of r, we can spot a nice simplification we can do. If we expand r in that function, we notice that it nicely simplifies to just being equal to the ratio between h and b. And since it is pointless to do that division twice, we can now directly use s to calculate the radius. We've been bouncing back and forth quite a lot. I hope I didn't lose you there. Let's update the graph in Desmos and see if everything still works. It works like a charm. We just have an error when b equals 0, since invalidates the division, but we cannot care for now. We'll handle that case once we move to Unreal to build the shader. The next step is to calculate the exact position of a generic point P on the segment, projected onto the circumference section. So, again, what we now want to calculate is another point on the circumference called PC tied to the position of P on the segment. If, for example, P lies on 2/3 of the segment length, PC should lie on 2/3 along the arc described by the circumference section. To approach this, we have to leverage the direct correlation we just noticed between the vertical distance from P and O and the angle along the circumference. The idea would be that since we know that the value of s corresponds to an angle of 90 degrees on that circumference, which equals to half p in radians, then py will correspond to another angle alpha, which is exactly the next thing we need to find. Since there is a direct correlation between them, we just need to impose that their ratios are the same and solve for alpha. Actually, since the y of p is expressed starting from the y of O, we should expand py subtracting from it oy. Thanks to this angle, we know in which direction the point PC is starting from the center C. And since we know the distance from that point too, which is r, we can say we found it. Note that the cosine must be negated because from C we have to move to the left, returning back towards the origin. On paper, everything looks fine to me, so let's head back to Desmos and update the graph to check if everything's done properly. It works, and seeing it move also feels pretty cool. So we finally know how to project each point on the circumference. But we're still missing something. I know, I say that every time looks like I'm about to wrap up a concept. To work out the math, we approximated the grass leaf to be a segment, but it actually has a thickness. That means the vertices in the actual mesh won't be lying on the line, but will be at a certain distance from it. Which means that their projected version won't be lying exactly on the section of circumference 2. They will be offsetted from the curve exactly as they are from the segment. To start accounting for that, we can add the generic vertex position V. And express P as it was a projection of V on the segment. Let's quickly add this change to the interactive graph. So now it's time to figure out how to find VC, the position of the vertex V once the grass leaf has been bent. We can start by noticing that if V and P are connected by an horizontal line which is orthogonal to the vertical segment, then VC and PC may be connected by a radial line that starts from the circumference center C and passes through P. This implies that VC may be calculated exactly as PC, but using a different radius value. If we project V on the same level of O, in fact, we can realize that we can simply add to R the horizontal distance between these 2 points and keep everything else the same. Moreover, we immediately realize that we don't need any more P and PC, since we're just interested in the final vertex position, and there's nothing that needs them to be calculated. Let's update the graph once again. Here, I'll actually keep P and PC for nice visualization purposes. Let's tidy up a bit this mess to wrap up everything. If we scan accurately the formulas, we can also notice something interesting in how alpha is calculated. It may be a bit tricky to see, but here we're actually multiplying Vy minus Oy by the reciprocal of the radius. So we can just divide that difference by r and scrap the variable s, since it now used only to calculate the value of r. Let's head back to Desmos once again for the final graph update. And that's how you do TechArt Blackmagic. It's now time to finally open Unreal and build the shader. Or maybe not. Maybe you already noticed, but until now we have been working in just 2 dimensions. Transposing everything as it is in a 3D environment would result in the wind able to blow only along one axis. Luckily, we don't need to do again all the math work to account for this, but just add few adjustments here and there. Imagine that now we're looking at the scene with a top view. This point is the grass leaf, and these are the world X and Y axes. The idea is to grab the horizontal components of our 3D points, X and Y, and transform them as the reference axis where the wind direction, which now is a 2D horizontal vector, and the wind tangent direction, another horizontal vector, orthogonal to the first one. That way, we can keep calculating the wind as it was 2D, and the wind tangent will store the vertices distance from the bending plane, so that we can add that back at the end. In other words, we could now see the process like not bending a line on a circle anymore, but like bending a sheet of paper on a cylinder. To do the transformation, we just need few simple vector operations. To obtain the component that runs along the wind direction, we have to do the dot product between the vertex xy coordinates and that vector. To obtain the second one, we have to do the same operation, but using the wind tangent instead, which, again, is obtained by rotating by 90 degrees the wind direction vector. And while we're here, we can take another look at our formulas and see if we can simplify our life even more. For example, we could do all the math locally to the origin O, so that its value is 0 throughout. To do that, we can just subtract it from the vertex position V right at the start, to obtain a local vertex VL. That makes possible a bunch of simplifications, like not needing C anymore, and the possibility of just using VL components in the other formulas where O was used. So now all our 2D bending process will look something like this. where before this we'll have to do the component's transformation to be oriented with the wind direction. And after, we'll have to recompose everything in our usual coordinates. Since Unreal uses the z-axis as up vector, this last bit could be confusing, but essentially the 2D x-axis has to become the first two components of the final 3D vector, while the 2D y component will directly correspond to the z component in 3D. And now I'll finally stop trying to melt your brain and implement all this stuff in Unreal. And that's it. Look at how bendy our grass blades are. Even if not exactly the topic of this video, I'd like to now spend some time in making our grass a bit better looking. Our animation could be the absolute best, but it would lose a lot if the rest of the shader doesn't please the eye. First of all, let's fix the height value. Right now, we just eyeballed it to something that looks about right, but we can do better. Sadly, there's no way of knowing the bounding box of an instanced mesh in Unreal that would have been perfect, since the last component would have given us exactly its height. Instead, we'll try to do our best to work around this limitation. We can start by looking at the height of the mesh itself and setting that as starting value. This is the height of the mesh with its default scaling. Now, we have to find a way to know if that mesh has been scaled when placed in the scene. We can do that with a simple trick. We can transform a unit vector that points in the dimension we are interested in from local space to world space and calculate its length. This will give us the scale along the z-axis of the mesh, so we can just multiply it by the height parameter to know the exact height of the instance in the scene. Very well. Now we can start by assigning a nice green value to our base color with some random variance. Next step is to create a gradient that goes from black to white from the root to the tip of the grass leaf. To do that, we can divide the object relative position by the scaled height. Be careful to keep this operation in the vertex shader, since most of the data we're working with in the pixel shader refers to instantiated mesh clusters. Then let's square the gradient to have a nicer curve, and let's use it for specular, roughness, and ambient occlusion, making each time the required adjustments. Now we're going to apply a well-known trick to improve the look of the grass in video games, turning the normals to the sky. Let's deactivate the tangent space normals for this shader, and let's try. At first glance, looks like the grass has improved, but the light behavior isn't that good actually. It's like all the grass was put on a flat plane. We are losing all the lighting variation the shape of the landscape should give us. Let's go get it back. To implement this fancier version of the trick, we'll have to follow a path that's a bit weird, but effective. We have to set in the landscape grass type asset the mesh to be aligned with the surface. This operation will cause all the instances to not be vertical anymore, causing some errors in our bend operation too. To fix that, we can straighten them back up by a shader code before applying the bend. To do that, we have to calculate in which position the vertices will be if the grass blade was placed vertically as before. Luckily, this operation will be simplified a bit by the fact that our mesh extends only across two axes, and the final position has to be perfectly vertical. Let's start from the object relative position and calculate at which distance the vertices should be from the mesh origin when in vertical position, along the local x and z axis. Now, the first component has to become a 2D vector, to retain the random grass blade rotation in the scene. Let's grab the first two components of the transformed x-axis and normalize them to have that direction, and multiply that by the value of the x and y components. Now we can append everything together and use these new positions as starting point for the bending operation. And now, as normal value, we can use the tangent space y vector, since it's the one that points from the root to the tip of the grass leaf in its original position. Let's now take a moment to appreciate the variety we got back in our scene. I'd say that now we should address the straightness of our grass, which doesn't look too natural. We can leverage the bending system we already got in place and see if we can find a way to bend each leaf in a different direction. Maybe we can set as bend direction the local right axis of each mesh after projecting it on the horizontal plane, so that each mesh will be bent on its own side. Nice. Now we should really break the monotony of the normals. They just follow the landscape without adding variety to it. To obtain what would be perfectly accurate normals for our bent grass, we can leverage the fact that we are bending it along a circumference. By multiplying the radius by the bend direction, we find the center of that circle in pivot relative space. Now, if we subtract it from the positions of the bent grass, we get a bunch of vectors that point from the circle center to the grass surface as rays. Let's pass them through the vertex interpolator, normalize, and multiply by the two-sided sign. And now we can interpolate them with our old upfacing normals to obtain the best looking effect we can find. As final touch, let's set the shading model to two-sided foliage. That was quite a digression, but we now finally got everything in place to start building a convincing wind, which actually reduces to properly animate only two values, bend direction and bend intensity. Before starting, I want to point out something though. The logic we'll use to build the wind will be kind of universal, good for basically everyone that wants to implement it in his project. The values of scale, speed, direction, etc. won't, as they have been selected to obtain a nice result on my personal scene, which will be surely different from yours. So gather all the patience you have if the result on your side won't be that good right off the bat, and take your time to adapt the shader to your needs. Let's start by creating a convincing gradient for the wind blows. In this case, since I want to keep everything as procedural as possible, I'll use this noise as base. Let's also temporarily set the shading model to unlit to preview the gradient we are going to build, to understand better what we're doing while we work. Let's use the object position, scaled as needed, as input. The idea will be that where the noise is white, the grass is fully bent by the wind, and where it is black, the leaves are near their rest position. Let's add a smooth step node to the noise, which will change the contrast curve so that the wind blows will be more decided, and will also remap the noise to 0-1 range at the same time. Now we need to animate the noise by translating it along the wind direction that we're about to define. For a reason that I'll explain later, I'm going to define the wind direction as an angle and not directly as a vector. So the value of 0 will correspond to the positive x direction, 0.25 to the positive y, 0.5 to the negative x, and so on. Let's now convert the angle to 2D vector by calculating its cosine and sine. Multiply this vector by a negatively scaled time, the scale to control the velocity, and the negative to not make the noise spun backwards, and add the result to the scaled object position. I've added a pan on the third dimension too to make the shape of the wind blows change with time. One last touch we can give it is to stretch it along the wind direction to improve the realism of the wind blows. Since the wind angle can be potentially set with any value, we have to find a way that will always work. We can't just stretch it, let's say, along the x or y axis. To do that, we can use the same approach we already implemented to our bending. Use the wind direction and the wind tangent to transform the object position xy components to a new base. Let's calculate the wind tangent vector by rotating by 90 degrees the wind direction. And let's do the dot product of both these vectors with the xy object position vector. And now we can just scale as we want one of these components to stretch the noise. After that, we can recombine everything back to the usual workspace coordinates by multiplying these values by their respective vector, adding the result together and appending back the third coordinate. Now that we are satisfied by our gradient, we can start using it to animate the grass. Let's set the shading model back to what it was before. Let's start by using the gradient as bend intensity parameter and to interpolate the bend direction between the rest position and the wind. On the far distance, I'd say that already looks quite good. But when looking nearby, the grass leaves are moving a bit weirdly. First of all, let's avoid them to completely straighten up when the gradient is black, by remapping the range of the wind gradient. Secondly, let's multiply that bend intensity by the length of the bend direction vector before it gets normalized. This way, the grass blades won't rotate around their pivot mechanically, but will have a more natural motion, like they are flipped over by the wind. As last thing, let's be sure we are never dividing by zero. Definitely much better. Let's have a look around. Even though it is quite nice, you'll agree with me that we're still missing something. The grass blades are missing some individuality, they're too synchronized in the oscillation. To add some variety, we can add some little random offsets and some oscillations to each instance. To do that, we need some randomly generated values, but, as you may already know, by default we are given just one of it, and we are already using it for the base color variety. There are probably infinite ways to generate pseudo-random values, which are less or more accurate and expensive. In this case, I'll go for the simplest thing I can do, and just use the object position component's fractional part. Since the instances are placed randomly in the world, we can leverage this thing to our advantage. Let's use the first value to make each grass blade to be a bit early or late in the wind blow animation. After that, I'd say to add some little oscillation to both bend intensity and bend direction. For the first, we can add a couple of sinusoids to the wind gradient, one slower than the other, which change influence depending on how strong is the wind in that moment. Easy as that, and we can already see the animation improving in the scene. Now, with the last random value we have, we are going to do something very similar to the wind angle. And that's why at the beginning I chose to express it as an angle first, so that now we can just oscillate it without going through a more complex vector rotation operation. So let's just add a very similar chunk of node to what we did before. One more thing, we can recycle this random offset to also make the rest bend direction oscillate. We can use the very same value as time input for a rotator node and pass that vector through it. And that's it, everyone. I hope you're still alive after this bombardment of information. What do you think? Is that something you will try to use in your game? How does it look to you? Do you have any doubts about this approach? There is so much more we could discuss here. We could still improve both on visual quality and performances. I can also imagine some of you skipping a heartbeat when seeing a grass field made of individual grass leaves. But more we move towards newer generations of hardware, more these kind of things will become a viable approach to take. And today I want to leave you with a challenge. If you were using a mesh that is not an individual grass blade, but a clump, what would you do to make the individual leaves still retain their individuality when animated? As usual, let's discuss it in the comment section. I'm very curious about your thoughts. And maybe we'll go deeper on this topic in a future video.